So, you guys know, what's the equation for the field from a point charge? E equals KQ over D squared. Why is it D squared?
Because it's a point charge.
It's a point charge, right? And we know that a point charge you spread in 2 dimensions. Now, we know also that if we had 3 point charges, Q1, Q2, Q3, each of those 3 point charges would contribute to the field at point P. Does that make sense?
Yes.
Now, if you wanted to figure out the total field at point P, what would you have to do?
You'd have to add up all of the fields.
Yeah, you got to do vectors, and it would be very painful unless you're a computer, and then you could have a computer do it, and it'd do it really fast, and you could do like 100 points and just like that. But to do this by hand would be a big pain in the butt. Well, that's for only 3 point charges. What if you had more than 3? What if you had, say, I don't know, 10 charged particles all in a line? Yeah, you'd have this big mess of a thing where you'd have to figure out each of those fields and add them all up. Now, you could use symmetry to do one side, and then the other side you just multiply it by 2 to get the total. But this would be a big, huge pain in the neck to figure out the net electric field at point P with 10 charges. But what if instead of having just 10 charges, I had, I don't know, how many atoms do you think are in this stick?
Too many.
Maybe, I don't know, on the order of Avogadro's numbers worth? So what if instead of doing it for 10 point charges, we did it for, I don't know, 10 to the 24th charges? How long would that take to do that?
I don't know if we have enough time in our lives.
Probably not, right?
Write a program.
Imagine, yeah.
Well, that's what he said.
Yeah, you could write a program for a computer to do it, but still, 10 to the 24th atoms, that's going to take a really freaking long time.
Even for just
Yeah. So, instead of doing that, what we're going to do is we're going to take advantage of the fact that, you know, calculus. You will drive yourself insane if you try to do it even for 10.
Drive yourself insane? Did you say that?
No, that was just my conjecture. That was, no. All right, so finding the electric field from a charged rod. Sorry, everything's funny when your nose is plugged up. Sorry. Finding it's a charged rod. We're going to use calculus. So setting up the integral. First step. Always. Jack, you ready for this? The very first thing you always do. Yeah.
I was like, so confused.
Why would I not be?
Draw a picture. Got to draw a picture. Because the picture is going to help you lay everything out. You're going to have about 3 different angles you're going to have to, or 2 different angles you're going to have to keep track of in this problem, and a whole bunch of different directions. So here we go. Draw a picture, put a coordinate system on the picture with the origin all along the rod. All right? Then we need to pick an infinitesimally small piece of rod. We're going to call that DL. So I'm going to take, here's my rod in my hand. I'm going to take a little piece of this rod. I'm going to call that little piece DL. All right? Why is it called D?
Because it's a small change.
It's a little piece. D stands for a little piece. An infinitesimally small piece called a differential, right? All right, draw a ray from DL through the point you want, and then you figure everything out. All right, so here we go. Example. This thing is a nightmare. So, here we go. First up. And by the way, when you do this in your homework, I don't care if you do an exact replica of what I have in the notes. That's okay, just as long as you know how to do it. Also, in 3 or 4 days, you're going to be taking a quiz on this. Guess what your quiz is going to be?
Exactly this note.
This exact same problem.
In 3 or 4 days, it's either going to be Saturday or Sunday.
Working days. School days, right. School days. So, yeah. This is the quiz. I am telling you exactly what's going to be on the quiz. all right, you're going to have a charged rod, an infinitely charged rod, and you're going to have to use calculus to determine the field at a certain distance from the rod. So here's how it goes. In order, first, draw a picture. When you draw the picture, you're going to want to draw your rod and then your coordinate system along the rod. Does that make sense? Second of all, it makes it a lot easier for you if you choose the origin as the center of the rod or the end. But don't do it some weird point, then the math gets all goofy. P is some point a distance away from the rod where you want to find the amount of field, right? Draw your little piece of the rod. This is your little DL right here. Length of the rod is capital L. Distance from P to the rod is D. DL is a little sliver of the rod. A little slice of the rod is DL. Now, then, that little sliver of the rod you pick, you're going to want it to not be in the middle. You're going to want to be able to draw a triangle from DL to P, right, at some angle, or else you're going to get confused and not be able to do the math. All right, so you want to draw it so you got your DL up here, P down here, and your rod kind of vertical like that. Sound good?
Yeah.
Now, what was the equation again for the electric field from a point? KQ over D squared, right?
Right.
However, what's my D in this case? From this point.
D sine theta. D divided by
Isn't it just the length of this hypotenuse right here?
Yeah.
So it's KQ over this hypotenuse, which is actually square root of D squared plus Y squared. Does that make sense?
Yeah.
So it would be KQ over R squared. All right, good. So a couple other things I put on my picture. I put on this angle, called that theta. Now, here's the reality. Do we care what the electric field is diagonally? No. How come? It canceled. The only electric field we really care about is the horizontal electric field. So it's the E cosine theta that we care about. Does that make sense? Yes, no? Because this is theta in here, right?
Oh, got it.
And we only care about the horizontal because the vertical component would cancel out. Because the field created by this would be perfectly balanced by a point down here that would create a field up, and so the up and down part cancel out. And so it's just the E cosine theta that we care about. All right? So the field that we care about, DE, in the x direction is actually DE cosine theta. All right? So that's how I'm going to start this problem. DE x in the x direction is equal to DE cosine theta. All right. Now we're going to start substituting stuff in. We know DE is actually KQ over R squared, right? Oh, by the way, I used 1 over 4 pi epsilon naught. I hope you guys are okay with that. K and 1 over 4 pi epsilon naught are the same thing.
Okay.
Did you guys know that? Raise your hand if you knew that already.
Yeah, let's write that down real quick.
Is K 9
Yeah,
times 10 to the 9th?
Yeah, K is 9 times 10 to the 9th, and epsilon naught is some constant. It's called the permittivity of the vacuum.
Yeah.
Yeah. Whatever. K and 1 over 4 pi epsilon naught are the same thing. Anyway, so it's K dq over R squared times cosine theta from before. Now, the next thing we know, we can say, well, this dq is actually a little bit of charge, right? But that little bit of charge, we know that dq over dl is equal to big Q over big L, right? Which means that dq is big Q over big L times dy. Big Q is the charge of the whole stick.
The small charge. Yeah.
Little piece, that amount of charge versus the charge of the whole thing is big Q. So dq is that little piece of charge. It's the ratio of that little piece of charge to its length is equal to the ratio of the entire charge to the entire length, assuming there's a constant charge density. So that basically means if your rod is 100 centimeters long and your charge is Q, that means if you have a piece that's 1 centimeter long, it's going to be 1/100th as much. That make sense? All right. So dq would be Q over L times dy in this case, because y is this axis. So we're going to plug in Q over L dy instead of dq. Good? So we got rid of dq. Now we're in dy because y is the variable we want to integrate over. Now, next thing. We've got to get rid of this cosine theta somehow, because y is our variable, theta is not. So we get rid of theta. Let's see, theta, cosine theta. Cosine theta, here's a triangle. Here's theta. What's cosine?
Cosine is
D over
d squared plus y squared.
Oh, d over r, right?
Yeah.
Would be cosine. So it'd be d over r, or d over square root of d squared plus y squared. So that's your cosine theta right there. And then lastly, we got to get rid of this r squared. Well, r is square root of d squared plus y squared, so r squared is that whole thing squared. So we've gotten rid of the dq, we got rid of the r squared, and we got rid of the cosine. That makes sense? Now all we have is a bunch of constants, and what's our variable?
Y.
Y. So we've got a dy, a y squared there, and a y squared there. So the resulting integral is this k q over L d over d squared plus y squared to the 3/2. And you think, oh my gosh, I need to know how to do an integral of something to the 3/2. No, you don't. No, you don't.
Because you have a template.
Because you have a table of integrals, and this is one they'll give to you.
Wow.
Like I said, the integration is easy.
It's easy because they give it.
Right. This is not a calculus class. This is a physics class. So the physics is all about the setup of the integral and keeping track of all your angles and all the cosines and all the d's and the y's and
So
the...
they
Yeah.
don't just care if you can integrate. They just want to know if you can set up.
Right. So there it is. There's the integral. And when you go through the math, this is what you come up with. K, Q, over d square root of L over 2 squared plus d squared. That's the answer.
So will we get the table on our?
Yes, I will give you the integral. All right, so you're basically going to take this
Okay.
and make that. Good?
Okay.
All right.
Okay, boss.
So you basically just work backwards.
Yep. Yeah, this is, like I said, this is a physics class. This is not a calculus class. There are certain integrals that you are expected to know, sine and cosine, and power rule. And that's it. Got it?
Yes.
So don't panic over the integration part. Panic over the setup. Yeah.
So it would work the same way if you chose your limits of integration as 0 and L, if you put the point on the end of the row.
Yeah.
Okay.
Yeah. Yeah, and then you multiply by 2.
Okay.
Or, yeah, right. Sorry.
Yeah.
Right, depending on the situation. Exactly. Okay, so here's the goofy thing. What we've just figured out is we have a stick. It's charged up with a bunch of positive charge. And we've got this equation. We've got this equation that looks kind of scary that says something about how strong the field would be at this point. Let's see if we can use some logic to figure out the equation, shall we? As you get farther away from this rod, as you get farther away from this stick, which has a length of L, what should happen to the field?
Weaker.
Should get stronger or weaker?
As you get farther away.
As you get farther away.
Should get weaker.
Weaker.
Should get weaker. Okay, so as D gets really big, what happens to E?
It gets smaller
How come?
because it's on the bottom.
D, oh, it's on the bottom, right. Okay, here's one for you. No, I'm not going to ask that question.
No, ask it.
Come on.
Try it.
Do it.
Do I want to ask this question?
Yes.
Try it.
Try it.
Give it a try.
You know you.
No, I'm not going to ask that
You
question.
want to hear our answers.
I don't want to answer. Okay. Ooh, very interesting question. What about this? What if, say this were a glowing like neon bulb or something like that, that was this long.
Okay.
When you're up close to the stick, it looks like a line, right? But what happens is you get farther and farther and farther away from this glowing stick.
It looks more like a point charge.
It looks more and more like a point charge. Would this equation look like a point charge if you were far enough away?
No.
Yes.
What the heck did I just ask you?
You asked if you're far enough away, if that equation starts modeling the equation for a point.
Yeah, what's the equation for a point charge?
KQ over
KQ
D
over
squared.
D squared. So what am I basically asking?
You're basically
Does that-
saying if the I was extremely, extremely small.
If what was really small?
No, if D was really big.
If-
D was really big.
If L was way, way, way smaller than D, what would happen to this equation?
It would just
Oh,
become.
that is L.
What would happen to this? What would happen to this term right
It would
here?
go away, and then you
That term would go
And then you
away.
have square root of D squared, and the
It would be Q over D times square root of D squared,
which is
KQ over D squared.
in the scheme of things, it's 1 point.
Does that make sense? Yeah. All right, so that's pretty cool. So this equation works. If L is really, really small, this stick is just going to look like a point, and it's just going to get weaker according to 1 over r squared. Make sense? Now, last question. What if, instead of L being really, really small, L was infinitely big?
L was infinite.
What would happen to this equation?
It would look like a plane.
It would look like a line, right? No matter how far back you go, it would still look like a line. All right, so let's see. So we're going to do this. We're going to adjust our equation just a little bit. We're going to say the limit as L approaches infinity of KQ over... Let's see, which of these two terms matters more, the D or the L? If
L is getting infinitesimally big, then the L matters.
then the D doesn't matter so much, right?
Right.
So we end up with KQ over D times square root L over 2 squared. So it's KQ over D times L over 2, or 2KQ over DL. Or, in other words, K times 2 over D times Q over L. What's Q over L?
That's the linear density of linear charge density.
That's the charge density. That's how many charge per length, right? Because L doesn't exist anymore, right? Because L is infinite.
Right.
But does Q over L exist?
Yeah.
What's Q over L? Like conceptually, what's Q?
Q's charge.
Charge. What's L?
Length.
You still have, for an infinite stick, can you have a value for charge per length?
Yeah.
Yeah.
Okay, let's ask this a different way. Let's say there were dots on the stick. Could you still have a value for dots per meter if the stick was infinitely long?
Yeah.
Yeah.
Absolutely.
They'd be like a straight with me.
So, if you can have a value of dots per meter, can you have a value of charge per meter for an infinite stick?
Yes.
So, what this is, then, Q over L is the charge density, which does exist even for an infinite stick. And so the answer is K2 over D times the charge density. Now, if you think about this, if you look at this carefully, That means the electric field is equal to 1 over d instead of 1 over d squared. Why is it 1 over d? For an infinite stick.
Because the charge density is going to be constant.
How many dimensions of spreading do you have? One dimension of spreading, so it's 1 over d instead of 1 over d squared.
Cool.
Got it? Yes.
When you were saying that the d goes, or the L goes to infinity, why did you get rid of the d squared but not the d on the outside of the square root?
Because you're still multiplying the d times that L term. Really, you're multiplying the d.
Wouldn't that be insignificant still?
So 0 times infinity? Remember? That's that weird limiting L'Hopital, all that garbage. Right.
So,
Yeah, no, conceptually what's happening is the reason the d plus L, the d goes away, is because if you add anything to infinity, if you add 0 to infinity, it's basically still infinity. But if you multiply 0 times infinity, then goofiness happens. And you got to use all sorts of different ways of thinking about it, like L'Hopital. Got it? All right, that's the lecture.